So what I'm going to do is take that thing that I had here and attempt to put a value k that now has a slider, and I can animate that as k is moving around. Let's just put a value of 1 though for now. I'll put k a value 1. And as we look at, let's turn off that curve. I still have the 0.55 here, which I need to get rid of. Right, that's better. So what I have is the function gx. I'm going to put g of x and k. What does it not like? Doesn't like something about that. You can't use k as a parameter because k is already defined. Oh yes, that's really annoying. So I'm just going to call it k1. Give it a different name. So what I've now got is a function of x and k, k1, don't matter, 2 values. That value of k, it's going to be, it's tunable, right? So what we do is in here we put k, and I need to plot g x comma k, and now we could animate that. So, you know, all of that's fine. I'm a little annoyed by the fact I've called it k1, so just I'm going to actually delete that and make that k, and delete that and make this one k1 instead. Okay, so we've got our function 2x divided by x plus k, and there it is wobbling around. It's not the complete function because we need the function that always makes sure that you get 1 back when you put 1 in, and obviously that's not happening right now. But if we put, say, x equal to 2, we can look at an example here and just try to work it out. If I put the value of 2 into this function, what do I get out where x is equal 1? Well, you can see that x is 1, so it's 2 over 1 plus 2. It's 2/3. So you want to divide the result by 2/3, and then you would get 1. This is normalized, yeah, to normalize it. So what you want to actually multiply this function by, you can see, you can work it out. And I'm going to just make some other function just to show this. I'm going to call this, say, h. And the function h is going to take a value k. I can reuse this because it's within a function. The value k, which is basically the inverse, that's 1 over, the value that you get from the function g as it stands at the moment, when x is equal 1. So in other words, it's k divided by 1 plus k, I beg your pardon, because I'm flipping it over. So we have x plus k, right? It's underneath. I'm putting it at the top because I need to flip it so that's the inverse as divided by 1. So 1 plus k underneath 2. So if I have the function 1 plus k over 2, if I multiply the function here, if I multiply it by that, I think it will normalize it. So let's see. And then we actually have a complete function, right? So what I'm going to do is that does what we want to do. So 1 plus 1 plus k. I don't know how to select a region. I don't know how to select a region here, so I'm going to use, using a touch screen. So, right, 1 plus k over 2. And that doesn't look good. I mean, it does normalize, but looks at the moment like we don't have a nice line. Oh, what happened there then? Well, I'll just hit play. And oh, so this is when suddenly a number of things became apparent. One is that if you do this, not all values of k are valid. I mean, some values of k will create a discontinuity between 0 and 1. That's not too surprising because, especially when you simplified the formula, you will see that for certain values of k, combinations of x and k, you will get an infinity. And let's not worry about that right now. More exciting is the fact that it looks like I can make it curve exactly the way that I want in either way. Let's see. As k gets bigger, it becomes a straighter line. As k becomes smaller, the line curves more. And between 0 and -1, it's invalid. There's discontinuities. So this is the first version of the normalized tunable sigmoid function. Later I developed a variant on this where k is a value between 0 and 1. It's very nice that way. -1 and 1. So if it's 1, you get maximum curve in one direction, and if it's -1, you get the maximum curve in the other direction, and there's no need for any infinities. And if you have a value of k of 0, you just get a straight line. It's perfect. You could call that the normalized tunable sigmoid function. But this was the first one. Well, we're nearly done on this first one because what I need to do though, I can just what I need to do is drag that, right, is I can simplify this. So what I will attempt, if I switch to the black, just bear with me as I do this. Uh, 2x over x plus k. I know what happened there. 2x over x plus k. So that's what we calculated, or what we found. The 2x over x plus k, and then the compensating normalizing factor to make sure that it always gives you 1 for a value of 1. So let's just do a little bit of algebra on this to simplify it, because there's a little bit of a mess right now. So if you're multiplying those two, you do that by multiplying the top and the bottom together of the two fractions. So this becomes 2x plus 2kx. Right? So it becomes 2x times 1 plus 2xk. And underneath we get 2x plus 2k. And I can see immediately that I can divide top and bottom by not 2x. I could divide everything by 2. I can get rid of the 2's. The twos will cancel out. So maybe I'll cancel them out like this. And so what you end up with is x plus kx divided by x plus k, if I haven't messed up anything. We'll see. X plus kx x plus k x divided by x. This feels wrong. But I don't think it is. It felt wrong. But that's the one. What a simple little formula that is. And by itself already it's useful. So let's x plus kx over x plus k. X plus kx divided by x plus k. You can see the properties of this. For any particular curve, you want to pick a particular value of k. Large values will get you closer to a straight line. K can be positive or negative, giving you a curve in one direction or the other. And as long as you keep out of the range for k between 0 and -1, so you want to stay out of this range. In that range it's invalid, as long as you stay out of that range. And when you examine it, you'll find that there's an interesting, fascinating property to this, which is that if k is equal 1, you will get a particular shape. Now, if we go 1, and that is 1 more than the minimum value of 0 of the range between -1 and 0. So basically +1, and you get this. If you take that -1 and you go back 1 to -2, you'll get the curve that goes the other way, which I found really interesting. It's like there's this weird region, but if you just got rid of that region, it's symmetrical otherwise. So I'll just show that. If we have an x of 1, So, you know what? I'm going to just create a function n. Okay. Like so. And we shall plot n x, and we're plotting for 1. And let's get rid of that that plot. So there we can see the curve. For a value of 0 we get 0, for a value of 1 we get 1. We've got a nice curve in between, and you can see the amount of curve that you've got there. So what I was saying is, right, between 0 and this is 1 more than the lowest value in the upper range of 0, right? Add 1 to it, you get this amount of curve. If you go negative, you have to start at -1. So if we go to -2, what do we get? That's a beautiful thing, because the two curves are can I get that up there? Those two curves are symmetrical. So it turns out that you can modify this function so that the actual curve is dictated by a value that it doesn't go from -infinity to +infinity, but goes from -1 to 1. And I will show that as well. Why not? We'll finish this session off.